I want to talk about transformations. There are three basic types of transformations: shifting, reflecting, and scaling. Now, shifting and reflecting tend to be the easiest ones, and for that reason, I'm not going to really focus on them. I'm going to really focus on the last one, which is scalings. But I just want to review because there's a couple properties that we're going to take into account when we're looking at scaling. So first, for shifting, there's two basic types. There's the vertical and horizontal. With vertical shifts, it behaves exactly as we expect it to. In other words, for instance, if I had some sort of function, whatever it is, I'll call it f of x, and I added 3, we expect that to vertically shift up 3, which is exactly what it does. It shifts up 3 units. Or when you subtract 3, it shifts down 3 units, just like we would expect. But for horizontal, which we pair with the x, it does the opposite of what we would expect. Instead of going right 3, which is what we think it would do, it actually in fact goes the opposite and goes left 3. And then for subtracting, the same. Instead of going left, it goes to the right. So I want you to keep that in mind when we get to scalings. It does the similar kind of thing. The vertical is more natural, it makes sense, but the horizontal does the opposite. I'm not going to get into why, but I'm just going to kind of get us to understand that basic concept, and we'll move from there. All right, for reflections, there's two basic types as well. There is reflections across the x-axis and then across the y-axis. X-axis reflections are the most common, and they're what we get when we throw a negative in front of the function. And a y-axis reflection happens when we put a negative next to the x. Now, there's no weirdness with those, pretty straightforward. Okay, so here we go, into scalings. Two types, horizontal and vertical. Now, I'm going to start with vertical, even though I wrote horizontal first, because just like with shifting, the vertical is more natural, okay? So for vertical scaling, what happens is if we multiply the whole thing by 2, what that does is it doubles the y values. So f of x, we say, represents y, and if we double all of the y values, what that does is it stretches the function in the y direction. So it stretches vertically. Makes sense. But if we put that 2 with the x, like how we do with the horizontal shifting, it does the opposite. Rather than doubling the x values, it compresses them. It would half them. So, I'm not going to get into the details of why. In your textbook, there is a discussion about that in section 1.7, but I find it to be really cumbersome. It's a little bit easier just to think of it like this. In the case with vertical and horizontal shifting, we just take for granted that it does the exact opposite with the horizontal cases, and that's going to be the same for us with scaling. When we expect it to double the x's, it ends up compressing them by that factor. Okay, so let me draw out some simple examples of this. All right. Okay, and let's say I'm just gonna do. Let's say we start at 2, 1. I'm going to do a little line segment and then go to 4, 2. Okay, so this is the point. 2, 1, 4, 2, and I'm just going to connect it. All right, this is my f of x. So let's say I do a vertical scaling. I multiply by 2. Again, f of x is y, so I'm multiplying the y's by 2, which means instead of going to 2, 2, 2, 1, it's going to go to 2, 2. And instead of being 4, 2, it's going to go to 4, 4. So 2, 2, 4, 4. So we see that the y values here have a difference of 2, whereas here they had a difference of 1. Makes sense. Really straightforward. Let's shift this up. We're going to do the same thing, except we're going to do half. And again, as I said, it's going to do compressing in the y direction. So instead of going to 2, 1, it's going to take half of the y values, and it's going to go to 2, 1/2. I'm going to write it over here for space. And then instead of going to 4, 2, it's going to go to 4, 1. It's going to take half of the y value. So in this case, the y values are going from 1/2 to 1. It's half a unit. So exactly half of the y values. All right, so totally clear. Makes sense. Let's move into the x's, or the horizontal scalings. If I put 2 next to the x, rather than doubling the x's, it halves the x's. So instead of being 2, 1, it's going to be 1, 1. And instead of being 4, 2, it's going to go to 2, 2. So here, the x's are a distance of 2, but here the x's are a distance of 1. It halves the x's. All right. Now, I'm just going to drive this point home. Shift this back up with some pictures on the graphing calculator. Now, I've already pre-programmed this all in. And I'm going to come back to the home screen here so you can see what I've put in. And I'm going to do the parabola, okay? So the basic parabola function. If I just graph basic parabola, x squared, there it is. Looks just like normal parabola. At the table, we're going through 0, 0, 1, 1, 2, 4, and so forth. It's exactly as we expect. So when I look at 2x, that's the vertical scaling, it should stretch the y values, or double the y values, right? So when I go to the graph, it's a skinnier graph. It's stretching along the y-axis. And if I look at the table, the y values are doubled what the y values are here. Okay, they're exactly doubled. All right, so let's come back over here. And if I do the same thing, but inside now, meaning a horizontal scaling. So we're putting the 2 inside. Let me select that graph so we could see it. Again, it's skinny. That's because, remember, it's compressing the x's. It's doing the opposite. It's not doubling the x's. It's forcing the x's to be smaller. So it's making it skinny as well. And when we look at the table, these x values are the same, right? But what's happening is the second graph, y3, is going through its y values quicker, which is why it's causing it to look skinnier. All right, but visually, it's compressing along the x-axis. So let's go to the halves. This is the half on the outside, so it's a vertical scaling of 1/2. That means it will compress in the y direction, in the vertical direction. There's my standard graph. And there's my slightly wider graph. All right, so it's made it squish down. It squished the y values, okay? And then for the horizontal scaling of 1/2, we'd expect it to do the opposite. Instead of halving the x's, it's going to double the x's. So it's increasing along the x-axis this time. Again, giving us a wider graph. Now, I want you to notice that this wider graph is not the same as the wider graph we had with the y's. So I'm just going to compare those wide graphs. In other words, the wide graph for the y's was the 1/2. Wide graph for the x's was the 1/2. So first is the vertical scaling. Now is the horizontal scaling. So it's not the same scale, okay? We are not stretching by the same amount, but it's causing the x values to double. All right. Okay, so I kind of summed this up onto a nice sheet here. What's happening in general. So if we have this general formula of A, F, B, C, D, okay? The CD, we know what those are. Those are our shifts, our horizontal and vertical shifts, which I wrote right down here. So I'll shift that up. Shift that up, get it? Okay, so the horizontal shift, that's the C. If it's bigger than 0, it shifts left. If it's less than 0, it shifts right. So it does the opposite of what we expect. When it's a positive value, it goes to the left. When it's a negative value, it goes to the right. I said that right. Okay, so for vertical, though, does the opposite. When it's positive, it shifts up. When it's negative, shifts down. Okay, Now, coming back to the scalings here. I also put the scalings in absolute values because if there are negatives with the scalings, that just does reflections across the x and y axis. So we're not talking about negatives or positives. We're talking about whether or not we're looking at fractions or whether we're not looking at whole numbers. So when we're talking about vertical scalings, that's the A. When it's bigger than 1, it's stretching vertically. When it's less than 1, it's compressing vertically. So is the parabola, it's stretching the values and making it skinny. But when it's compressing, it's squishing the y's down and making it wide. Okay? For horizontal, does the opposite. When B is bigger than 1, it's compressing horizontally. So it's forcing the x's squishing the x's. That's why it's skinnier. But when it's less than 1, it's stretching the x's. It's making them wider. And so we kind of have this basic picture, doing the opposite, but in essence, it ends up kind of behaving similarly in terms of widening and stretching. I hope that helps.